All right, so welcome back, everyone. So today we're going to talk a little bit more about the composition of molecular clouds and go into some details about the chemistry that's going on inside of there. Also talk a little bit about deuterium fractionation that is also occurring. So if you were to think about, well, what is the main component of molecular clouds? Obviously, hydrogen is clearly going to dominate. And for hydrogen, that's either going to be the atomic or molecular forms. But surprisingly enough, the saturated hydrides, and in those kind of cases, I mean things like water, ammonia, and methane, these are not necessarily going to dominate because you might think, well, if we have a whole lot of hydrogen around, that's clearly just going to react with any available oxygen, nitrogen, or carbon, and then just keep going until we make up the fully protonated versions of those neutral molecules. But as we're going to be seeing, there's very complex chemistry that's actually going on. We're forming, even though they are fairly, simple molecules, at least from an organic chemistry standpoint, they do have, more variety than, simply just protonated elements going on here. Also, as we have been seeing, unsaturated radicals and ions are also very abundant. And the other thing is, because of the very low densities, things are not necessarily going to be in thermodynamic equilibrium. So because it can take hundreds to millions of years for the concentrations and everything to equilibrate, you can very easily find non-equilibrium conditions inside of these clouds. And for this reason, kinetics are also going to be very, very important. In fact, when we start looking at some of these spectroscopic surveys, they actually reach what's known as the confusion limit. Essentially, there's just way too many transitions, you have overlapping, and then of course, the source that you're looking at is not one discrete source. There's actually many discrete sources there. So you see a little transition, but then you see a neighboring transition. Well, that could be very easily from a different little point source in the cloud, which is, in front or behind of the other source that you were looking at. It could be traveling at a different velocity. Therefore, the transition is going to be moving at a different, have a different Doppler shift on it. So it becomes very, very difficult to identify all these little lines, especially the very, very weak ones. So that's a major problem with this. All right, and just as an example of some of the varieties of the molecules, here's the Orion KL star forming region. And essentially what we're looking at over here is a whole bunch of different microwave transitions. So again, we're basically dealing in the 200 to 800 gigahertz region over here. So obviously we have things like formaldehyde, sulfur monoxide, silicon monoxide, carbon monoxide, cyanogen, that's the CN, carbon monoxide, carbon monosulfide, and then even more complicated molecules, as you go along here. So there's many, many molecules, even things like methanol, fairly complicated molecule, but will form fairly readily in interstellar space. And even we see over here, we even have things like deuterated water as well also show up. And we're going to talk a little bit more about how we can actually even see some of these deuterated compounds as well. And then here's just a blown up region of some of the spectra. So as you can see, obviously the big line's very easy to point out, but these radio telescopes have enough resolution that you can start basically picking out all these individual little lines. And while the big ones and the moderately big ones can very easily be assigned for the most part, a lot of these other little ones down here are essentially just down the noise. And these are real transitions, but they're simply just too weak, and it's just very difficult to make a conclusive identification. So really, a lot of these things down here are essentially just unknown transitions for that. And I mentioned this was the Orion KL region. Well, here is Orion, and if you ever look up towards the Orion constellation in the night sky, you'll see kind of this fuzzy blob if you're around Orion's belt there. And the KL region is the center region right here. So that's where a whole lot of interesting chemistry is going on, and basically you got some dense clouds and everything going here as things are collapsing. And then that's just a little big blown up region of the KL region here. So it's a very active, dynamic region of the Orion Nebula here. All right, so what are some of the interstellar molecules that have been seen? And this is not necessarily a complete list, but at least gives you an idea of some of the types of molecules that have been seen here. Obviously HCl, so obviously hydrogen has been seen, no problem. HCl, so protonated chlorine, water, N2O, HF, carbon monoxide, silicon monoxide, sulfur dioxide, OCS, ammonia, silane, diatomic carbon, methane, carbon monosulfide, silicon monosulfide, hydrogen sulfide, phosphorus nitride, sodium chloride, aluminum chloride, potassium chloride, aluminum fluoride. So really, these fairly simple diatomics, have been seen pretty readily. Then here we start having some carbon chains, and then you have carbon chains with halogen on the end there, or silicon. Here we have basically these carbon chains with a nitrogen on one end and hydrogen on the other end. Then again, you could have varieties of this with a little bit more hydrogen stuck on there and a longer carbon chain. So here you got your HNC, and then you got just with sticking some oxygen or sulfur on the end, HN with a bunch of carbons on the end. So you got these varieties, and again you got acetylene and ethylene as well. Here we have your aldehydes, your alcohols, your ethers, your ketones, all over here. So basically your simple organic compounds that show up quite readily in interstellar space. And a lot of these, especially like these, can be very unstable. But if there's nothing reacting around there, they can have decent quantities of these things around here. So you got here, dimethyl ether. You have acetone. So really all those simple molecules are present there. There's formic acid as well. Here's just a little continuation of some of these molecules. We even have cyclic ones as well. Here we have some molecular ions, and we did talk about some of these before. Here we have hydronium. There's of course H3+. That's over there. The carbon monoxide cation, and then a whole bunch of radicals. Essentially just carbon chains with a hydrogen on the end. And everything. Now, a lot of these compounds and radicals and everything that have been seen, these have been done through rotational lines in the microwave region. And that whole thing with the confusion-limited spectroscopy and stuff, that was all done in the microwave region. So in other words, these are all rotational lines where these things are very readily identified. And because of this, we are missing a lot of the possibly symmetric molecules that have no dipole moments because it can be easily missed. Notice right here, as I have my different carbon chains going on, and again on the previous slide, I had these chains over here with a whole bunch of carbons and then nitrogen on the end. You would expect, well, why don't we see just like a whole long chain of just plain carbon right in a row? Why do we always have like a carbon chain with a hydrogen on the end, or a carbon chain with a nitrogen on one end and a hydrogen on the other, or possibly without one? And the reason for that is all these compounds have dipole moments. If you just had a pure carbon chain, there would be no dipole moments, and you could very easily miss that. So in this kind of a sense, any like molecules that don't have any rotational spectrum, and because of that, any things without dipole moments can very easily be missed. And you'd basically only be able to see those through things like electronic transitions, and those in many cases are a little bit harder to come by for a whole bunch of reasons. Basically, just hard to get enough resolution to accurately identify those, and electronic transitions tend to be a little bit more on the broader side as well. So it makes identifying a lot of these molecules in the visible spectrum actually pretty difficult for those things. But again, some of them have actually been seen as well. I mean, if we look over here, C3, that has been actually seen. C2 again has been seen there, but these are few and far between because they're kind of special cases. But for especially these longer ones, where they're only identified in the microwave, you need to have some kind of dipole moment present for them. And that's also why if you look over here, like your acetylene and your ethylene, these were identified in the infrared, not in the microwave, because again, they wouldn't have a rotational spectrum for those. All right, so what is the composition of some of these dark cores? And by dark, this means that it's very, very opaque to the light. So that means that these things are generally going to be fairly cool and dense, and there's not going to be much light coming in from the outside that penetrates all the way through. So here are two dark cores, just kind of comparing them and seeing how they're similar and different here. And we look at this, carbon monoxide, and then some of these simple radicals and ions, they have similar abundances. So we kind of look, here obviously the carbon monoxide is the same. The hydroxide radical, they're pretty close-ish. The protonated carbon monoxide, bang on. The protonated nitrogen, bang on. Ammonia, they're about a factor of 10 off there. Some of these other molecules are going to be fairly close with this. So a lot of these up here, are going to be fairly close. But where they start diverging is actually when you get down here. Also, like I was saying here, these oxygenated compounds, these are also going to be pretty close abundances there. So really what this is telling us between these two different molecular clouds, the chemistry is that's forming these particular compounds is going to be very, very similar. So that tells us something about that. So your prediction routes and rates are going to be essentially identical for those. And for the simple ones, like just your few little atoms there, this is mainly going to be in the gas phase for the simple ones, and then for these more complex ones down here, this is going to be more on the grains where these things are actually forming, because it would be very difficult to have just the right elements bump into each other just at the right time to form these more complicated molecules here. So more likely what's going to happen is you have these things on grains, and then you have them subjected to ultraviolet radiation, cosmic rays, and you form some radicals. The radicals bump into one another, and then you finally get your more complicated molecules coming off of the interstellar grains there. Now, what we do notice over here is for the TMC, which is the Taurus molecular cloud, we notice that these carbon chains are actually more abundant over here. So notice here for the C2H, those are identical. The C3H, those are pretty close. But here for the C4H, this is like a factor of 10 more abundant over here, and then these are seen, and then down here, these aren't even registered. So these are obviously going to be more abundant. And then here for the HCN and the carbon chain derivatives with the nitrogens on the end, you can see that these are all significantly more abundant over here than they are for the L134 cloud. So basically that means that whatever is occurring for the simple things is pretty much the same, but there is something different going on here for these more complicated chains, or the more longer chains of carbon going on down here. All right, now as to what is actually going on between these two, there's not like one nice agreed mechanism or origin for these, so there's not a simple answer that can explain the differences between these two clouds here. All right, and remember I said TMC1. Well, here is the Taurus molecular cloud. So this is essentially the cloud we're actually looking at over here. And then this is for the L184N. It's also called L183. I'm not exactly sure why it has two designations, but they are synonymous. And this right here, this obviously is your little dark core, the dark cloud core over here. But as you look at this in the mid-infrared, it's actually glowing, and this glow is actually coming from a light scattered off large dust grain. So, in the visible and other radiation regimes, it's absorbing all the radiation, so nothing's really getting out. But of course, it is still a bit warm side, so there is some mid-infrared that's actually being scattered off. So actually, it's what they call a core shine over here for that. Okay, so how can carbon chains form? Well, inside of clouds, most carbon is in the form of carbon monoxide, and that's how it's kind of locked up. So we need some way to liberate the oxygen from the carbon, so this way the carbon is able to form more complicated molecules. So cosmic rays can act to actually liberate the carbon, but it's not going to be by, the cosmic ray bumps into the carbon monoxide and then it splits up into two pieces. Actually, what happens is that the cosmic rays excite the hydrogen molecules, and that's that Lyman-Werner transition. We talked about this in the before times, before the spring break. And in that kind of case, the hydrogen gets excited to a stable state and then decays to basically an excited vibrational state, which then breaks apart and in the process emits some far ultraviolet radiation. And that far ultraviolet photons that come off, those dissociate the carbon monoxide. So remember, inside these dark cores, there's not much in the way of light from the outside world or the outside universe that actually makes it inside of there. So really cosmic rays by exciting hydrogen molecules are the only way we get infrared radiation, not infrared, ultraviolet radiation inside of the cores there, so they can actually react with the carbon monoxide. So when this occurs, basically the ratio between liberated carbon to carbon monoxide is 1 minus whatever the albedo of your of the dust grains are. Usually that's around like 0.5. Times the abundance of your carbon monoxide times the abundance here of the oxygen-containing compounds. And typically for most cores, this comes out to about 6 times 10 to the minus third. So a little bit less than 1% will actually be in the form of the liberated carbon compared to the carbon monoxide. But that's good enough to start the whole reaction chain going. And also cosmic rays can also bump into helium atoms, producing helium ions, which bump into carbon monoxide, and then there's a charge transfer, the oxygen gets kicked out, and then you're going to form carbon ions as well, but this is not as efficient as the far ultraviolet photons that are being produced up here. Now, once you have your liberated carbon, again, there's going to be plenty of H3 plus around. This is going to react to form the CH plus, and then a hydrogen molecule will come off of there. Now, once you have your CH plus, that can very easily react with another H2 molecule to make your CH2 plus, and then another hydrogen is liberated. And then your CH2 plus can react with another hydrogen molecule to make CH3 plus, and another hydrogen is eliminated. And then you might think, okay, well, I'll just keep going. Here's my CH3 plus an H2 to give me CH4 plus an H. But it turns out that this reaction over here is actually endothermic. So this one is really not going to proceed for that one. So this one doesn't happen. But what can happen is the CH3 plus can react with an H2 to make the CH5 plus. And after electron recombination and everything, this can go and very easily form methane molecules like that. So this would basically be how methane molecules are formed in dense molecular clouds there. Now, CH5 plus is actually a really interesting molecular ion. The transitions have been measured over 20 years ago, but as far as I know, they have not been assigned. They're basically nearly impossible to assign because the transitions are just way, way, way too messy. Just as a comparison, here is methane and then the methyl cation, and you can see nice patterns over here that even people who aren't very good at assigning spectra could still pick out the patterns here and kind of assign things. Meanwhile, the CH5 plus, this is essentially grass. There are no nice patterns actually going on here, so trying to figure out where your bands are and everything is essentially impossible to assign. Now, how was this CH5 plus made? Essentially, you just had a methane hydrogen mixture, and the H2 was about 50 times the methane concentration. And from there, the H2 would make H3 plus, the H3 plus reacts with the methane, and then we get the CH5 plus, and then the hydrogen, and then you just record all the little transitions that are there. All right, so why is CH5 plus such a major pain to actually assign? Well, unlike methane, which has, its very nice 109.5 bond angles and, very nice carbon-hydrogen bond lengths that are all nice and consistent, for the CH5 plus, it's a complete chaos over here. Essentially, what happens is that while you can have one stable structure, the barrier between these different possible stable structures is ridiculously small. 29 wave numbers. So these right here, they basically just kind of transition between these two stable structures. And then there's this other structure over here, the little C2V structure, which is only 341 wave numbers. Again, that's still fairly on the low side. So you can basically transition here. You have this structure, you have this structure, you have this structure, you have this structure, and they're essentially all interconverting between one another, and it makes things very, very difficult. Really, the best way of thinking about this is a carbon atom which has like a little swarm of hydrogen atoms flying around it. So it's really more like little mosquitoes flying around the carbon atom than having a nice rigid structure that you might have for like methane or even the methyl cation over here. And because there is no nice structure, it's essentially in all these different possible vibration, all these different possible structures. Therefore, it's going to have a whole bunch of overlapping vibrational bands, and hence you get a gigantic mess. There's a possibility that if you could go and rotationally cool these things down and vibrationally cool them down, you could get a much better spectrum over here, and you could eliminate a lot of these lines and basically focus more on the structures which are most stable in the lowest energy states over here. And there has been some work towards that, but still, even after eliminating a lot of these lines, it's still very, very confusing spectrum. But that's one of the work that they're still continuing on for that. All right. So anyway, back onto our carbon chain. So how do we form longer and longer carbon chains over here? Well, once I have my methane made, this can very easily bump into a carbon ion over here, and then we can make C2H3 plus, which essentially is like a protonated acetylene plus hydrogen, or we can make the acetylene cation plus an H2. There's those two possibilities that can actually form there. And then once you have your C2H2 plus, this can very easily bump into another H2 and basically make our same ion up here. So basically, at the end of the day, you can make your protonated acetylene fairly readily in interstellar space. So this is essentially the beginning of your carbon chains. And then once you have yours over here, you have your electron recombination, and this goes and neutralizes it, and then you just form regular old acetylene, and then the proton comes off of there. And then once you have your neutral acetylene, well, this can bump into a acetylene cation, and then make a C4H3 plus or C4H2 plus, limiting how many hydrogens you need. And essentially at this stage, we're starting to build up our carbon chain. You could also have, here's your acetylene, you could easily bump into another carbon plus, and then you can make a C3 H2 as well. So there's many possibilities. You're really only limited by, well, your imagination and the physics, of course. Here's another possibility: carbon plus a C2H2 gives us a C3 and an H plus another hydrogen, which comes off. So then once you have you could also have your C2H plus an acetylene, that gives us a C4H2 plus an H. You could have your cyanogen plus your acetylene gives you the HC3N plus H. So, basically you just take, these similar type of reactions over here and you just, rinse and repeat them as much as you need to, and you will eventually grow these chains over here. So these are essentially gas phase reactions for the most part. But again, they could also be occurring on grain surfaces as well. So it's really a combination between these two things. But you have to realize if these things are actually growing on grain surfaces, they're not going to really leave the grain surfaces. So these have to some way be liberated from the icy mantles that are on these dust grains. So they basically need to heat up to liberate these higher molecular weight compounds, or these things need to be forming in the gas phase. So there's a possibility of totally gas phase, or forming on the gas phase, forming on the grain surface, and then being liberated as the molecular cloud heats up. So there's possibilities either way for this. All right, so next up we're going to move on to deuterium. So as you know, deuterium is of course the heavy isotope of hydrogen, and it has a abundance of around 10 to the minus 5, 10 to the minus 4. It depends exactly where you're actually looking here. And all the deuterium that's in the universe today was produced during the Big Bang nucleosynthesis. Any deuterium that is around now that is present in stars is actually being burned during the nucleosynthesis as the hydrogen burns to produce helium. But while technically some deuterium would be produced in the cores of stars, it is very quickly reacted as helium is formed. So there's not any efficient production mechanism for deuterium in the modern universe here. So now, interestingly enough, as we look at the D to H ratio in our solar system, we notice that it is not consistent. There's actually quite a bit of variation going on here. So one, there's down here we have this represents Jupiter, Saturn, Uranus, and Neptune, and these are essentially the protosolar or interstellar medium ratios down here. Now, Jupiter and Saturn, you can see why. These have essentially the protosolar parts, because these would be just as like when the sun was forming, these were essentially gathering up a lot of the hydrogen gas and everything that was actually present in the solar nebula when our solar system was forming. So that's why these essentially have abundances which are closer to what you would expect in the interstellar medium. Now, on the other hand, Earth and some comets, and then Enceladus, this is a moon of Saturn over here, they have much higher D to H ratios. So that means they have more deuterium than you would have over here. So there's some enhancement that's actually going on with these different molecules. So what's actually causing this enhancement? Well, there's a couple of things. First of all, these are the D to H ratios that are observed in water over here, and also down here as well. And the reason we have a little bit more deuterium present is because as the water is forming, deuterized water is going to be a little bit heavier, so it's going to be a little bit harder to actually evaporate off. So that means that just like distillation, your lighter components are going to boil off first, and your heavier components are going to be left behind. So as we're talking about water here, the lighter H2O is going to be more readily boiled off, and you're going to be left with the heavier HDO and D2O as well. Mainly when we're talking about the DH ratio, this is mainly just in the form of HDO in those kind of cases. So as these things heat up in the early solar system, a lot of these things basically boil off the lighter H2O. Meanwhile, for the gas giants in our solar system, these have essentially the original concentrations from the what the solar nebula would have had, because they're cold and they really haven't had much opportunity to boil off the water as they get towards the warmer areas of the solar system. A lot of remember these comets and everything, a lot of them have visited the inner solar system quite a bit, so they have boiled off some of the lighter waters as well. So for the gas phase reactions that are occurring, there's also a isotope effect we have to consider when talking about the deuterium fractionation that is actually occurring. So as you may know, heavier isotopes, these have a lower 0-point energy, and the reason for this is essentially when we're talking about bonds between atoms, the vibrational states can basically be approximated, or I should say are related to the square root of our spring constant, which essentially is how strong our bond is, which for different isotopes is going to be exactly the same, but then we just divide that by the reduced mass between the two atoms. So essentially, as you have your isotope, your mass is increasing, in other words, going from hydrogen to deuterium, this right here is going to lower the frequency of those vibrations down here. So essentially, as we're seeing here, for diatomic protium, or regular old hydrogen, this is going to be up here. When I have HD, this is going to be reduced. The energy difference over here works out to be about 410 Kelvin for that. And then between the HD and the DD, this is about another 500 Kelvin below where the HD level is here. So as you add heavier atoms, the lowest vibrational state, or the location of the lowest vibrational state, is decreasing. Now, the 0 point energy over here is due to the fact that we can't actually have our atoms at the bottom of this potential well. Is actually because of the Heisenberg uncertainty principle. So remember, that's your uncertainty in position times uncertainty in momentum is greater than or equal to h bar over 2. Well, if I had my atoms exactly at this position at the lowest point of the potential well, I would have exact knowledge of what my position is and also exact knowledge of what my momentum is. And that violates the whole Heisenberg uncertainty principle. But now if I have the 0 point energy up here, now there is some uncertainty in the position of these atoms, because they basically can vibrate back and forth like this. So there's going to be a little bit more uncertainty in position and uncertainty in momentum. And now Heisenberg uncertainty principle is all happy with that. And remember, momentum is mass times velocity. So if you have very light atoms up here, you're going to need more velocity to counter that. So therefore, you're going to need a higher 0 point energy up here to fulfill the Heisenberg relation. Meanwhile, if you have higher mass over here, you can now localize these things a little bit more, because your mass is increased, so therefore you need less velocity, therefore you need less 0 point energy actually going on, and therefore you can be a little bit lower in there. So that's why if you try localizing an electron, it's very, very difficult, but if you try localizing a macroscopic object, it becomes very easy, because the mass is so much larger, so we can very easily have much better accuracy for that. So that's that 0 point energy. And essentially what's going on here is, as you increase it, you're going down to a lower 0 point energy. And therefore, if you have a reaction where you have to try to liberate either a hydrogen or a deuterium, well, see, this hydrogen, that only needs, in this case, 431.8 kilojoules per mole to dissociate. Meanwhile, if you're doing this with two deuteriums, you're going to need an additional 10 kilojoules per mole to kick that out. So all things being equal, especially if you're dealing at things at the same temperature, it's going to be much easier to break apart the H2 than it is going to be to break apart the D2, right? So that's why, for this reason, deuterium is going to be stickier than hydrogen in a reaction. So if you have, equivalent, a deuterium or a hydrogen, which one's going to leave? The hydrogen is going to be the one that's more likely to leave. Deuterium is going to stay around. And because the deuterium is a little bit stickier, this means that deuterium is going to wind up actually building up in molecules. So that's why we can actually see enhancements actually going on here. Now, this works best when we're dealing with very cold temperatures. If you're dealing with very warm temperatures, then the difference over here is going to be fairly minute, and you're not going to see much enhancement actually going on. But if you're dealing with very, very cold temperatures, this is when you actually have that enhancement occurring. And this is why this isn't seen everywhere. It's only going to be seen in dense molecular clouds. So what is the basic reaction that's occurring here? Well, we have some protonated cation over here. And then this can very easily bump into an HD molecule. If it bumps into a regular H2 molecule, well, nothing's really going to happen here. But if it bumps into an HD, well, there's the possibility of it, either just exchanging the proton, or taking the deuterium for the proton here. And it turns out that the deuterium sticking to some other atom is going to generally be more exothermic. Well, it's actually always going to be more exothermic over here, because of the stronger binding between the deuterium and the whatever atom this is here. So this is going to be an exothermic reaction. So therefore, if I have some protonated version bumps into this, we get the deuterated version of that. This also occurs for H3+. So I form my H3+, it bumps into an HD, very easily form my H2D plus hydrogen, and this is exothermic by 178 Kelvin. So this is why I said this mainly works when you're dealing with very cold sources. If you're dealing with something that's warm in the several hundred degree range, well, this essentially is going to be forward and backward. You're not going to have much enhancement. But if it's very cold, it's going to definitely prefer the deuterated H3 plus over here. And in fact, when you're dealing with just thermodynamic equilibrium, the ratio here between the H2D plus and H3 plus is equal to the HD to H2 ratio, so that's going to be around your 10 to the minus 5 or so, times e to the, your delta E over KT. So again, if you're dealing with temperatures which are, maybe 10, 20 Kelvin, you're basically going to have this, 178, divide that by 10 or 20, you're going to get something that's like, e to the ninth over here. So this value is going to be, very, very large, and that's going to enhance this, and you're actually going to have concentrations of H2D plus, which can be, comparable to that of the H3 plus, in fact, even greater than 1 for some of these reactions here. All right, so essentially when you're dealing with clouds, where your temperatures are, on the order of 10 Kelvin, which would be like e to the 18th or so, your H2D plus can actually be much, much greater than your H3 plus concentrations there. Now, this little thermodynamic equilibrium here, this is totally ignoring other species, because again, once you start forming these, this can start reacting with, other species like carbon monoxide or whatever, and that can, definitely reduce these concentrations here. So that's that one thing here. This is a very, very simplified, oversimplified model for this. Also, this is ignoring electron recombination as well, because again, that's going to essentially break this apart, the H2D plus and as well the H3 plus as well. So deuterium is going to very easily transfer to other molecules or ions. So here I have, the H2D plus carbon monoxide. This can give me DCO plus H2. The rate here is going to be 5.37 times 10 to the minus 10 for that. Or the other possible reaction here could react and give us the HCO plus HT. And here the rate is 1.07 times 10 to the minus 9. Now notice that this rate over here is about twice what this rate is. And if you think about that, this means the reason is only basically statistical. So here I have 2 hydrogens and a deuterium, right? So therefore, 2/3 of the time I should get this, 1/3 of the time I should get that one. So that's why this rate over here is basically 1/2, because this is, a half of 2/3, of course, is 1/3. So this is going to be half of that rate. Okay, so just because the rate over here is actually slower, that's not actually accounting for the thermodynamics. We're talking about the kinetics down here, not the thermodynamics. You have to realize, those are two different beasts, and we have to be careful with that. Now, as for the kinetics of this, again, we can take a look at our, H2D plus to H3 plus ratio. That's again going to be our, HD to H2 ratio here, and then this is looking at the forward rate of reaction, and the forward rates of reaction and the reverse rate of reaction. This is looking at this reaction. So the H3 plus HT gives us the HD2 plus the H2 at our 178 Kelvin. So this is, again, just looking at the forward and reverse rates. Now, when we're dealing with very low temperatures, the reverse rate is going to be very, very small. So that means, of course, when I have this molecule bumping into an H2, it's really not going to go in this direction. But again, it will very readily go over in this direction here. So our forward rate will be very big. Therefore, I can kind of just ignore the Kr over here. And the Km value here, this is essentially the Langevin rate constant, or rate coefficient, when the reaction with a species M is occurring. So in other words, when you have your H2D plus over here bumping into something and protonating or deuterating it, basically whatever is going around here and destroying it, right? So just so we're on the same page, this is the formation rate. All these down here are the destruction. So either reverse reaction, bumping into an electron and breaking apart into hydrogen and H atoms and H2 molecules, or this is being destroyed because it's protonating some other species like carbon monoxide or whatever. Now, carbon monoxide is like the highest non-hydrogen concentration usually seen in clouds, and that means that when clouds get really, really cold, which can happen at around 10 Kelvin, the carbon monoxide is starting to be frozen out. It's basically freezing onto dust grain surfaces. And when this sink of the H3 plus and H2D plus gets depleted, then we start having even higher enhancements of the H2D plus actually being seen. So when you remove one of the destruction mechanisms, this of course causes an enhancement of the H2D plus. Okay. Now, we're talking over here about, one deuterium. Well, why can't this, just continue on? Well, you very easily could do that. You could have H2D plus an HD to make HD2 plus, another hydrogen. This is also exothermic by 190 Kelvin this time. And then you can take this one, bump it into another HD, and we can make D3 plus. And this again is exothermic by 230 Kelvin this time. So all these are exothermic. So really, under the right conditions, you can actually take your H3 plus and basically like lock up all of your deuterium in the form of D3 plus here. right? And the very coldest locations. It's very, very possible that you could have concentrations of D3 plus, which are actually higher than H3 plus. And there's actually been some searches for the D3 plus, and as far as I can tell, there hasn't been any successful observations of D3 plus, mainly because remember we talked about H3 plus a few weeks ago. H3 plus was very lucky in terms of observations that it's in an atmospheric window. So we basically can just put a telescope and then look without having to worry about any interferences from things like water, carbon dioxide, and that's in the atmosphere. Unfortunately for D3 plus, again, with the whole isotope effect, its transitions get shifted by a little bit, and when that happens, the transitions are now in one of the water windows. So it makes it very difficult for ground-based observations for this. So that's why it hasn't been seen yet. There has been a couple of trials to look for it, but as far as I know, they were basically had some bad weather and couldn't see it. But theoretically, at least, D3 plus should be able to be observed. There are other ways of fractionating beyond just the H3 plus. We could very easily have our methyl cation over here, and this can react with the HD, and then there could be a little bit of an exchange reaction going on here to make the CH2D plus H2. This is exothermic by 375 Kelvin. The acetylene cation could also react with it to make the C2HD plus, and this is exothermic by 550 Kelvin. So both of these are more exothermic than the initial H3 plus reaction that we saw. So that means that these fractionations could be efficient in hotter clouds. So when you get eventually too hot, the fractionation of the H3 plus using the HD over here is not going to be quite as efficient because now the reverse rate is going to be comparable to the forward rate. So that's not going to be very good. But that means that these steps over here are going to start taking over, and then you can have fractionations in warmer clouds because these are even more exothermic than the H3 plus reactions are. All right. And by hotter clouds, we're talking about 60 Kelvin. So still ridiculously cold, but on the scheme of molecular clouds, relatively warm. And now here, you might be wondering, well, does this also occur for very cold clouds? Well, it's not going to be as important for very cold clouds because here the H3 plus is going to be basically dominating in concentration over these hydrocarbons over here. So colder clouds, H3 plus dominates. Warmer clouds, it's going to be one of these hydrocarbon changes going to basically dominate. Okay, so what are some species that have actually been observed here? Well, here we have the D to H ratio, again, around 10 to the minus 4, 10 to the minus 5, generally. Here are these I and OI. These are basically just different types of protosolar clouds and stuff that these have been observed in. Here again, there's the HD to H2, around 10 to the minus 5, 10 to the minus 6, somewhere in that vicinity. And then again, we got protonated nitrogen, protonated oxygen, and deuterated. And you can see that, remember these, again, we're talking about 10 to the minus 4, 10 to the minus 5 in that region. Notice these concentrations are way, way above that. So there's definite fractionations and enhancements going on here. Here, this is like 1% of that. Here we have doubly deuterated water is actually like 5 times 10 to the minus 5. Now, think about this. This right here should be around 10 to the minus 5, but we have essentially a factor of 10 to the 5th enhancement for a doubly deuterated water. Again, we have some more of these, maybe around 1%, maybe even up to 10% or so. Again, a lot of these are running around a couple of percent regions for the protonated carbon monoxide. Down here, again, here's the H2D plus. This is around 3 times 10 to the minus 3rd for that one. Here's the singly deuterated water. The numbers are all over the place. A lot of this depends upon exactly, the different clouds you're looking at, how old it is, how cold it is. So, these variations are not too surprising. It all depends upon, the actual local history of the cloud in there. Here's protonated hydrogen sulfide. You can see that, this, or I should say this regular old hydrogen sulfide in this case, that's up to like 15%. Here we have the doubly deuterated carbon sulfide. That's like 33%. Here we have formaldehyde. That can be, again, up to like, let's say 12%, or, even in these kind of cases down here, it's actually even more abundant than the regular old formaldehyde. So in fact, the deuterated variety is actually more abundant than the protonated variety of formaldehyde. Here, and this was actually one of the most surprising ones over here. We have ammonia which is regular old NH3, and then deuterated ammonia, fully deuterated, 3 deuteriums in there. Now, just from plain old statistics, you would expect, well, if this is 10 to the minus 4, 10 to the minus 5, this should have an abundance of around 10 to the minus 12, 10 to the minus 15. But we're seeing, abundances over here around 10 to the minus 4th, 10 to the minus 5th, around there. So that means we essentially have, a factor of 10 to the 9, 10 to the 12th enhancement of the deuterated ammonia versus regular ammonia there. So, this is, just, amazing, when you just kind of think about, the amounts of enhancement that are actually seen there. This is just singly deuterated ammonia. Again, these actually have abundances in some cases, a couple of percent to, even comparable to, the regular old plain ammonia. And here we have doubly deuterated ammonia. You got this one, about 3 to 27%. This one's like about a factor of 0.5%, here 2 to 4%. So, again, these are, dramatic enhancements compared to, background. And again, we got, some more protonated hydrocarbons. Here's another very interesting one, methanol, right? So here we have regular old methanol and then the CD3OH. This one has about 0.1 to 2% compared to regular old methanol. So again, that's just amazing, the amounts of enhancement that are actually seen there. As far as I know, they haven't seen fully deuterated ammonia. It turns out like it's easier to put the deuterium over here on the carbon than it is to put the deuterium on the oxygen. I think there's like an easier shuffling that the deuterium rather goes to the carbon than the oxygen. So like even if the deuterium ends up here on the oxygen, it like gets shuffled over to the carbon for that. So that's why usually don't see like a partially deuterated here with the OD on the end. Again, here you got the CH2DOH versus methanol. So again, you got pretty good abundances here. Here we just have one deuterium, and this is the only one which is on the oxygen. But here we got a couple of deuteriums on there on the carbon again. We got pretty substantial enhancements. And then here we have our carbon chains with the deuteriums on the end. And again, we can see that we have substantial enhancements for all of those things there. All right. So the temperature is really dependent upon how efficiently this deuterium fractionation actually is. So actually over here, this is observation of the D2H+. So this has actually been seen. So these are actually just two of the transitions for the D2H+. It's still a little bit harder to actually observe. Now the interesting thing is H3+ could not be observed in the microwave region because it has no dipole moment. But of course, if you take one of the hydrogens and make it a deuterium, you've killed the symmetry, and now there is a dipole moment, so therefore there's a rotational spectrum, so therefore you can see this in the microwave region. So D2H+, H2D+, both of these can be seen in the microwave region, and this is where they're actually have been seen here. H3+, of course, can't be seen. D3+, of course, also can't be seen there. Now, as for where we're most likely to see these deuterated molecules, again, the colder areas, these are going to have the most enhancement that's actually going on. Also, if you deplete the amount of carbon monoxide, that is also going to enhance the amounts there because carbon monoxide is a very efficient way to react away a lot of the other molecules to form like DCO plus and so on. So cold areas, not a lot of carbon monoxide. And when I say these are being depleted, a lot of that means it's just freezing out onto ice grain surfaces there. And then basically, here's just kind of like the scheme on how you can do some of these fractionations. H3+ can very easily just react with these molecules, but then again, basically just have the same thing, except now we have the H2D+, HD2+, D3+, and it can very easily go and deuterate some of these. But of course, if you have H2D+, you could very easily have either the DCO+, HCO+, N2D+, N2H+. It really depends upon your statistics. But in some cases where you could actually have even more D3+ and H3+, that would have 100% of the time you only deuterate things over here. And then over here, this is just looking at how much fractionation is going on as a function of the radius. So in other words, how far you are from the center there. Notice that as you get closer and closer to the center, the fractionation increases quite a bit. And that's because as you get towards the interior of the clouds, that's where it's the coldest, that's where it's the most dense, so therefore these reactions are going to be very efficient, and you're going to have a lot of fractionation going on. As you get to the exterior of the clouds, it starts warming up out there, and things are very easily broken apart, and you're not going to have as much fractionation going on. Now, interestingly enough, as your cloud evolves and warms, so what you're going to happen is your fractionation is going to disappear because quite obviously we don't have deuterated water on Earth. We have regular old water with very small amounts of deuterium in there, enhanced a little bit, but still relatively small. But what's going to happen is a lot of these deuterated molecules, if they're frozen on grain surfaces, as the cloud starts warming, those molecules are going to start evaporating. And when that happens, you're now going to have an enhancement that is basically outside of your thermodynamic equilibrium. So you're going to have a lot of deuterated molecules in fairly warm clouds, but they haven't had time to actually reach thermodynamic equilibrium yet. All right, and actually this is what I was just saying. So cold temps, the deuterated molecules, they freeze onto your dust grains, and eventually your collapsing core will heat up. And by heating up, we're talking in the 150, 250 Kelvin range. This is called hot molecular cores. And now these molecules are evaporating. These are going to cause high D to H ratios, which are about 100 times over background. And then this occurs before your thermodynamic equilibrium can be reestablished. So you're going to be seeing things which are kind of like out of whack, but it's just because you're kind of like in that transition region as the cloud is doing its final collapsing and warming up. All right, so the last one I was a little bit over the hour mark, so I'll stop it here, give you a little bit of a break. And otherwise, we'll continue this up next week, talking about diffuse interstellar bands and dust. And otherwise, just keep washing your hands, stay healthy, and I'll talk to you later.